What if I told you that this bubble helped build a $40 billion empire? It's not just air, it's science, secrecy, and a whole lot of style. Let's crack it open. In the glowing pantheon of consumer products, few items have achieved the cultural ubiquity and commercial might of the Nike Air Max. But behind that sleek bubble is a secret science lab, a design revolution, and a billion-dollar gas problem. To the casual observer, it's a sneaker, a stylish, comfortable piece of footwear that has graced the feet of everyone from presidents to Premier League footballers, from hip-hop moguls to suburban teenagers. It sits on a store shelf, an inert object of desire, but to understand its true significance, you must look past the supple leather and breathable mesh and peer through its famous window into the heart of a technological marvel that took aerospace engineering, architectural disruption, and billions of dollars in research and development to perfect. This seemingly simple bubble of air nestled in the heel is not just a design quirk. It is the engine of a global empire. It's a proprietary technology so complex and so fiercely guarded that its creation happens within the walls of specialized, almost mythical facilities. This is the story of how that bubble is born, and how a complex dance of chemistry, pressure, and industrial might transforms raw plastic pellets into a cultural icon. Strap in, this is the story of a sneaker that literally runs on air. But before we dive into the billion-dollar bubble, go ahead and hit that subscribe button. Think of this like making a spaceship, if that spaceship was also comfy enough to run a marathon in. Before we enter the high-security sanctum where the air unit is forged, we must first understand the vessel it inhabits. The creation of the main body of an Air Max sneaker is, in itself, a marvel of global logistics and manufacturing precision, a process known in the industry as cold cement construction. Unlike the old world, high-heat vulcanization used for simple canvas shoes, the cold cement method is what allows for the use of modern, lightweight performance materials. It begins, as all things at Nike do, with design. In the sprawling, state-of-the-art campus at Nike's world headquarters in Beaverton, Oregon, designers sketch, render, and model. They obsess over every line, every texture, every colorway. These digital blueprints are then translated into technical specifications and sent to one of Nike's vast manufacturing partners, typically in Southeast Asia. Here, the first stage is the cutting room. Massive rolls of material, premium leathers, engineered mesh, synthetic suedes, and high-tech textiles are laid out. Computer-guided hydraulic presses or laser cutters then descend, stamping out the dozens of individual pieces that will form the shoe's upper with unerring precision. These flat components then move to the stitching lines. In a symphony of whirring needles and focused skill, armies of workers assemble the upper. It's a complex, three-dimensional puzzle. Stitching connects the main panels, high-frequency welding bonds synthetic overlays without a single thread, and reinforcements are added to high-stress areas like the eyelets. Simultaneously, in another part of the factory, the sole is being prepared. This consists of two parts, the midsole and the outsole. The midsole is typically made from a lightweight responsive foam like EVA, ethylene vinyl acetate, or PU, polyurethane. Pellets of this material are injected into molds and heated, expanding to create the cushioned chassis of the shoe. A cavity is left in the heel, a space reserved for the crown jewel. The outsole, the durable rubber layer that makes contact with the ground, is molded separately with its iconic tread pattern. The key moment is the lasting. The completed upper is steamed to make it pliable and stretched tightly over a foot-shaped mold called a last. Once secured, it's often sent through a cooling tunnel, which shrinks the material to create a snug, wrinkle-free fit. Now the shoe finally has its shape. The two main components, the lasted upper and the sole unit, are ready to meet. Both surfaces are meticulously cleaned and coated with a special primer, followed by a powerful proprietary cement. After a brief trip through a drying tunnel to activate the adhesive, the two halves are carefully aligned and joined by hand. The shoe is then placed in a series of hydraulic presses that apply immense uniform pressure from every direction, ensuring a permanent bond. The cold cement process is complete. After a final quality control check, lacing, and a quick clean, the sneaker is boxed and ready for its global journey. That's the normal part, but now we're entering Nike's Area 51. No cameras, no leaks. Just pressurized magic and serious sneaker voodoo. What separates the Air Max, what makes it a legend, is what happens thousands of miles away from those Asian assembly lines back in the United States. The Air unit is not outsourced. It is a state secret, created exclusively in two high-tech, heavily guarded facilities. The Nike Air Manufacturing Innovation, Air MI centers in Beaverton, Oregon and St. Charles, Missouri. These are not mere factories. They are cathedrals of science. Within these walls, a workforce of 1,300 specialists, including PhDs and dozens of engineers, oversees a process that is more akin to building a component for a spacecraft than a shoe. It all begins with a material called thermoplastic polyurethane, or TPU. Delivered as raw pellets, this specific polymer blend is Nike's secret sauce, engineered for the perfect balance of flexibility, durability, and gas impermeability. These pellets are melted down and extruded into thin, continuous sheets of TPU film. This is where the magic starts, through a process called blow molding. Imagine a far more sophisticated version of blowing glass. The TPU sheets are heated until they are soft and malleable. They are then fed into a complex steel mold, which clamps shut around them. Pressurized air is then blasted into the space between the sheets, forcing the plastic to expand and take the precise, three-dimensional shape of the mold, creating the iconic hollow air unit structure. This blow molding technique, perfected for the Air Max 93, was a quantum leap. Prior to this, air units were made using a simpler thermoforming process where the shape was largely dictated by the pressure of the gas inside. Like inflating a balloon, blow molding gave Nike's designers the freedom to create self-contained, architecturally complex shapes that could fit the curvature of the foot, leading to the 270-degree bubble and beyond. Once the unit is formed, it moves to the inflation stage. A specialized needle injects a highly pressurized gas into the hollow TPU bag. For years, Nike used sulfur hexafluoride, SF6, a large molecule gas that was excellent at staying trapped within the TPU membrane. However, in a move driven by environmental concerns, SF6 is a potent greenhouse gas. Nike invested over a decade of research into re-engineering the entire process. Today, the air units are inflated primarily with nitrogen, the most abundant gas in our atmosphere. The challenge was immense. They had to develop a new TPU film and a new bonding process that was robust enough to contain the smaller nitrogen molecules. After inflation, the unit is sealed with a powerful high-frequency weld, but it's not ready yet. Every single air unit is subjected to a battery of relentless quality control tests. They are squeezed, pounded, and flexed by machines for hours on end. A famous set of these devices, known internally as Kim testers, named after the daughter of air technology's inventor Frank Rudy, simulate the impact of a runner's foot strike over and over, ensuring the unit won't burst or leak. Only after passing this brutal inspection is the air unit deemed worthy, packed and shipped to the assembly factories in Asia to be placed into its foam throne. The complexity of the air unit isn't just for show. It's the solution to a series of profound engineering challenges. The primary problem is one of physics. How do you contain a highly pressurized gas within a flexible membrane that will be subjected to thousands of violent impacts, equivalent to hundreds of pounds of force every single day? The material must be strong enough not to rupture, but elastic enough to compress and return energy. This was the puzzle that aerospace engineer M. Frank Rudy first brought to Nike co-founder Phil Knight in 1977. His concept was brilliant, but it was Nike's legendary designer, Tinker Hatfield, who transformed it from a hidden technology into a cultural phenomenon. Inspired by a trip to Paris, where he saw the Centre Pompidou, a building famous for exposing its internal structural elements on the exterior, Hatfield had a revolutionary idea: cut a window in the midsole to make the air unit visible. This was met with corporate panic. Marketing executives were horrified, fearing a visible bubble would look weak and be easily punctured. But Hatfield's team solved the engineering challenge by reorienting the seams on the air unit, moving them to the top and bottom instead of the sides, creating a clear, stable window. With the release of the Air Max 1 in 1987, industry was changed forever. Technology was no longer something to be hidden, it was something to be celebrated. This sparked an internal arms race at Nike, a relentless quest for more air. Each successive Air Max model was a testament to overcoming another manufacturing impossibility. The Air Max 180, 1991, eliminated the foam between the air unit and the outsole, creating 180 degrees of visible cushioning that made direct contact with the ground. A daunting durability challenge. The Air Max 93 used a new blow molding process to create the first 270-degree unit, inspired by the shape of a plastic milk jug handle. The Air Max 95 was a watershed moment, introducing visible air to the forefoot and utilizing a dual pressure system, firmer cushioning in the back, softer in the front, requiring two different air units to be precisely calibrated and embedded in the same sole. This evolution reached its zenith with the Air Vapor Max, which did away with the foam midsole entirely, attaching individual air pods directly to the upper. The entire sole is the air unit, a feat of design and manufacturing that was the culmination of 3 decades of innovation. From the guarded walls of the Air MI facilities to the final assembly line, the journey of an Air Max is a story of two halves. One is a tale of global manufacturing at an immense scale. The other is a secretive, almost alchemical process of scientific innovation. Every time you see that bubble in the heel of a sneaker, you are seeing more than just air. You are seeing the legacy of an aerospace engineer, the vision of a rebellious architect, and the relentless hum of a proprietary industrial machine that turned a simple, brilliant idea into a multi-billion-dollar icon. If you've ever worn a pair of Air Max, hit that like button. Want more untold stories behind how things are made? Subscribe to the channel. We've got more drops coming soon.